All right, let's take a look at test three, some of the review here. So I included, uh, first off, two other videos with the essay questions that are derive the law of sines. Okay, one, derive the law of sines. And then you're going to use that to solve a problem. And then the second essay question is to derive the area of a triangle formula, the trig form of it. Derive area of a triangle, area of a triangle, trig form. Okay, and the third will actually use law of sines, but it'll be much more difficult. I'm just going to put LS. It'll be a difficult problem. Remember, choose two of those three. So I already created videos for both of those. So that will not be included in here. And the second one as well, you also have a problem to solve one problem. Okay. All right, so in this one, what I'm going to focus on is the inverse trig functions first. And I think it'll go long enough, and then I'll make a part two with some of the other stuff. So first, graph sine inverse, or I may ask you to graph cosine inverse. I could actually ask tan inverse as well, but I'll just say it's going to be one of those two on your exam. And before we graph that, remember, first off, that this does not mean 1 over sine. Okay, I know the negative 1 exponent, typically we think 1 over, but trig is special, right? It does not mean that. So an inverse, recall, you switch x and y, right? So the best way to think about this is, well, if I asked you to graph y equals sine x, right, and then just change the domain and range, switch x and y, change the domain and range. That's how I would approach it. Now, you can also use your calculator. I don't have it pulled up here, but that's okay. What I caution, right, use your calculator as a check. There's still many students not scaling your axes, and I'm not testing can you input things in your calculator and give me a poor graph. I'm testing, do you understand the trigonometry and what you are doing, right? I want to see you truly understand trig, not plug and chug in a calculator. So on that note, let's look at sine really quick. Okay, I'm going to do the very short version of this. Let me go just a little bit longer here because this is an old topic, right? So you should know that sine starts here at 0, 0, and we get one full period at 2 pi. Now, of course, there could be transformations, right, with amplitude changes or period changes and shifts, left and right, up and down, all that good stuff. I will say on the test for the inverse functions, I am not doing any transformations. I just want to see, do you have the basics down? Okay. And we also know that sine begins at 0, 0, and then it heads up to 1, and then back down to 0, right? And then down to negative 1, and back up to 0 when we get 2 pi, and that's the one full period. All right, so if we switch x and y, remember from pre-calc, there's a problem here that we wouldn't have a function, right? A one-to-one function, when we do an inverse, it has to be one-to-one. And a one-to-one function has to pass the horizontal line test, and it fails right there. So what happens is we have to go back a little. We don't need the full period, but it's easier to graph right that way. We only need to write here negative pi over 2, because after that, again, it will not be one-to-one. Okay? So we want to look at, I'm going to erase this. This section here, we restrict the domain to keep it one-to-one. And all in all, I mean, there are infinitely many points there, right? But in this section from x negative 1 to 1, but really three key points will do the trick. those three there. I have negative pi over 2, negative 1, I have 0, 0, and I have pi over 2, I guess I didn't write that, 1, right, that point, pi over 2, 1. So if I'm changing the domain and range, if I'm swapping x and y to get the inverse, then instead of range negative 1 to 1, I'm going to have a domain negative 1 to 1. Right? And instead of the domain negative pi over 2, to pi over 2, I'm going to have that as the range. This may not be exactly to scale, but that's fine because the x and the y, right, don't have to be on the same units, just like we graph sine. So now if I take those 3 points, 0, 0, if we change it, right, flip x and y, it's still 0, 0. But if I change these two, then I'm going to go back 1, right? I'm going to go back 1 and down pi over 2. This point is negative 1, negative pi over 2. And similarly here, 1 pi over 2, when we change the x and the y, we do the inverse. Right? And then there's curvature here, right? There's curvature here. There will be curvature up here. I'm not too concerned how accurate you are there. You can use your calculator as a check. You know, it's going to look something pretty close to that. That's what I am looking for. Okay. Are there other points, you know, along here? Yes. But just like when we graph the basic function of sine, I didn't find pi over 4 and root 2 over 2, right? I know that point exists, but we just kind of sketched that region. Same thing with sine inverse. All right, going a little quicker, cosine. Right, again, that graph. Now we actually can look just from 0 to 2 pi because cosine starts up at 1. Right? It starts here. And then 1 full period is 2 pi in length. Therefore, at negative 1, I'm going to be down here, the halfway. Right, and this graph is going to do this. Of course, both of these do extend indefinitely, but I'm not looking at graphing these. I want the inverse. Okay. So if I restrict the domain to keep it 1 to 1, I need to look only here. Again, we have 3 great points. I have 0, 1. This is pi over 2, right? So pi over 2, 0. And then pi negative 1. Do the inverse, change your x and y, and graph those 3 points. So instead of 0, 1, I now have 1, 0. So I'm going to go over 1, up 0. Okay, scale your axes, write the units. Okay, I mean, I know it's unitless, like we actually do have radians and then just values, right? But write the numbers, write the scale. Okay, 0 pi over 2. So this one, in fact, will head up here. There's pi over 2. And then negative 1 pi is my other point, negative 1 pi. All right, so cosine actually stays above the x-axis. Cosine inverse, I'm sorry. So thinking of its domain and range now, the domain of sine inverse is from negative 1 to 1, and the range is from negative pi over 2 to pi over 2. The domain of cosine inverse is negative 1 to 1. Those are the same, right? But the range is from 0 to pi. A quick picture to help remember this, like when you're doing inverse trig and you need to think, is it in the domain or not? We usually think of sine and tangent. When you're looking at the unit circle, your values will come here. Okay, you need to go negative pi over 2, so quadrant 4, and up to pi over 2, quadrant 1. Both sine inverse and tan inverse use that. Okay, use those two quadrants. While cosine, you can see down there the graph, right? On the unit circle, we're going up to pi, so that's quadrant 1 and quadrant 2 for cosine inverse. All right. So keep that in mind as you do problems. Remember that sine inverse and cosine inverse can both be done on the calculator. However, I always want exact answers, so if it is on the unit circle, if it's a special angle on the unit circle, you should have those exact values. There are the graphs. Let's move forward with a few examples in the same section. All right, we are going to look at how about this example in the current textbook. It's number 40, but that's irrelevant, section 7.4. Doesn't matter. I want to look at sine inverse sine 2 pi over 3, one example. I want to look at about tan inverse, tan inverse negative 4.2. And we'll do one more kind of like these. How about cosine inverse of pi? Sine pi. Switch it up. Oh geez, I cannot write. Cosine inverse sine pi. There we go. Writing the problem is the hardest part for me right now. All right, then we're going to get a little more complex here. We're going to do, how about tan cosine inverse 3 over x. And the last example we will look at is tan sine inverse p over square root p squared plus 9. All right. First thing you want to think about with all of these is what should your answer be, right? If I'm saying sine inverse here, I know my final answer should be an angle. I'm just going to write theta for angle. Okay, when I do sine, I'm going to get some number, right? So I'll do the inside, I'll get a number, and then that final answer should be an angle. In this next one, I actually do tan inverse first. So this will give me an angle, and then I do tan of that, so the final answer will be a number. All right. Now, both of these, you know that an inverse and its function, the function and an inverse, should cancel, right? Like square root and squared cancel. However, you have to keep in mind the domain. Okay, they're always check domain. So yes, I want to say these should cancel, right? Sine inverse and sine cancel, but checking the domain, still can't write. We have a problem because sine inverse 2 pi over 3, okay, think of that range, right? We only have negative pi over 2 to pi over 2. So that result, we cannot find sine inverse of 2 pi over 3, right? Because it's not within the allotted domain. So we don't in fact cancel. This is not pi over 3 here. Okay, not true. But we can still evaluate it because sine of 2 pi over 3, right? Think of your unit circle, 2 pi over 3. I always need a quick sketch, is this angle here. And sine is y, so that's negative 1/2 and root 3 over 2. So root 3 over 2. So now if we do inside verse, square root 3 over 2, sine inverse of that we can do, right? These should always stick with quadrant 1 or 4 because this is positive. I know I'm in quadrant 1. So the angle who has a sine of root 3 over 2 is going to be, let me change colors here, it's going to be that angle, right? Because that has this coordinate, and that is 60 or pi over 3. So that is our final answer. Okay. Again, be careful of domain. Now you can, of course, check. You could plug this all in your calculator and make sure you're in radians and, whatever pi over 3 is, it's 1 point something, right? And that will give you the approximate answer, but I always want exact. So use your calculator as a guide, no problem with that, but know how to do the problem, make sense of it. Now this next one, I want to do this though, because tan inverse negative 4.2, like we can do that, right? It will have a value, but I have no idea what it is. It's not a value that is a special angle in the unit circle. So plug it in, you'll notice these do in fact cancel and you will get negative 4.2, oops, 4.2, not 4.1. Again, you have to have a calculator for that one, so makes sense. All right. Next, cosine inverse and sine, those don't cancel, right? Yes, this is an inverse, but it's not the inverse of sine, it's the inverse of cosine. So that's why, all of these really think about the domain and go through the process anyways. It's just good practice, good habit. All right, sine pi. Sine of pi is 0. So cosine inverse of 0, the angle that will give us 0 for cosine, remember cosine is x, is up here, right? It's pi over 2. Okay, nice and easy. Actually, let's throw one in here. What if we actually reversed this, but let's do cosine sine inverse root 3 over 2. All right, kind of piggybacking off of that first one we did. So sine inverse root 3 over 2, as we stated in red right here, right, we have that answer. It was pi over 3. So cosine pi over 3, so cosine of that angle is 1/2. Right? That should do it for all of these, going back and forth from all your trig functions, inverse to the regular function or regular function to the inverse. Okay, just break it up like normal algebra, right? PEMDAS, order of operations says to do inside parentheses first. All right, these next two though, like what the heck is this, right? We don't have that on the unit circle because I don't know what x is. Maybe it is. I mean, a special angle, I should say. Maybe it is, maybe it isn't. Same thing here. Like, I don't know what that is. But thinking of inverse, this says, tell me the angle, right? We're going to get an angle here whose value would be 3 over x. Well, since I'm dealing with cosine, that's adjacent over hypotenuse. So the way I like to approach these is I have some angle who will have a cosine a over h, right, 3 over x, and what I have to do with that is tangent. So what is tangent theta? Well, tangent is opposite over adjacent, right, but I don't know opposite. So I could get opposite by doing Pythag. I'll just call this side b, right? A squared plus b squared equals c squared. So 3 squared plus b squared equals x squared. And b squared equals x squared minus 9. B is plus or minus square root x squared minus 9. All right, quick tip. These will always come out. You're not going to need the negative. Right? The reason being, think of cosine inverse. We had just talked about how cosine inverse falls quadrant 1 or 2 only. Right? So if this side here were negative, that means the y would be negative, and I'd be either down here or down here. And that doesn't happen. Right? These will all happen where we're going to stick in quadrant 1, okay, quadrant 1, and keep everything positive. That's the short story to that. We could get into it more, but for simplicity's sake, keep it positive, stay in quadrant 1. All right, so if that is B, now I have opposite over adjacent, right? If the question was to do tangent, then tangent of that new angle is opposite square root x squared minus 9 over adjacent over 3. That is it. That is your solution to the problem. There's nothing more you could do. You can't simplify that. All right, one more example. This one's a bit uglier, but same process, right? Sine inverse gives me a theta. Tan will give me a number, so I should have a number, and it could include variables. So the angle theta, who will give you opposite, right? Opposite over hypotenuse, p over square root p squared plus 9. But I want tangent again. By the way, we could have done any of these. Like I could have changed this to cosine. I could have changed that to tan. I mean, it really doesn't matter. I would do the process the same for each of these. Okay, I need tangent, which is opposite over adjacent. Again, I don't know a side, right? But we have Pythag. I'll just call the adjacent a. A squared plus p squared equals square root p squared plus 9 squared, right? C squared. Simplifying this, we have a squared plus p squared equals p squared plus 9. Subtract your p squared. Those will cancel. So a squared is 9, which means a is plus or minus 3. But again, we don't need the negative. And once again, you could see it. Sine inverse would be in quadrant 1 or 4, right here. But if a were negative, that means x is negative, right? Would be in quadrant 2 or 3. So it doesn't work. We only need to deal with the positive. All right. So now we are done because tangent of that angle, right, of theta, is opposite over adjacent, which is p over 3.